as you can see, I have made this agent-based modeling framework in JAX. I'm supervised by my supervisors Marcel and Ahmed, and I'm Siddharth. So let's get into it. First of all, what is agent-based modeling? I guess people here are really familiar with it, but just for people who do not know, like if your model has a lot of agents, if they act autonomously, they interact with each other, they interact with the environment, then perhaps your model is an agent-based model. Uh, so how is it used? Is basically these individual agents are modeled as simple as possible and but how they interact with each other, complex phenomena just arises automatically. And in this context, there is this famous Breitenberg's rule of uphill analysis and downhill invention, which means that it's really hard to analyze something which is complex just by observing it, but it's easier to analyze something which you make using small blocks, and then you have complete control of that thing. Uh, ABM has been used to model these amazing applications, power grids, population spread, swarm robotics. But all right, what are the challenges in ABM? It's like modeling many agent systems is computationally very expensive. Many agent meaning like thousands of agent or something. And advances in machine learning, like neural networks, are kept far away from ABM because we do not have the tools to do things like automatic differentiation through these models. That's where comes in JAX. Now, what is JAX? Many of you may have heard this across a lot of talks. It's like a jittable, vectorized, and a autograd library built on top of Python. Jittable meaning if you run it once, the other runs will be really fast by some computational shortcuts. Vectorized meaning one function will be just vectorized through all the inputs. And autograd meaning if you have a forward graph, you can just differentiate through it and you'll get gradients. It was used in 2022 in Pure JAX RL to show that it can speed up end-to-end reinforcement learning 40,000 times. It has an interface just like NumPy. I'll just present a very small example of what it can do, how we can use it. So let's say we have a function f which takes sine of x, which goes into it. All you need to do to vectorize this function in JAX is just say jax.vmap, that function. And all you need to do is to make it jittable is just do jax.jit dot that function, and that's it. So this is as easy as it gets. The only caveat is that f should be a pure function. Now, what is a pure function? The size of the parameters going inside the function do not change in size. These are some useful libraries, EOJAX, EOSAX, and JAX MARL, which fits this context. Now, okay, in FORAGAX, what is the novelty which I have programmed? It's basically you can step, so you have many agent systems, so these are all agents. So you can step these agents simultaneously, like in a vectorized way. You can select these agents, select some of these agents to do something. Okay, I select agents who have energy more than 5 or something. This can also be vectorized and jittered. You can sort these selected agents, and you can add agents and delete agents on the fly without breaking the VMAP and JIT, which JAX provides us. So which speeds the simulations of many agent systems by a lot. The reason you have these blue dots is because you also need to simulate the blanks to maintain the pure the characteristics of functions to be pure. For the programmers in here, I tried making a very basic UML of this framework so that you know what is behind the under the hood. So you start by two classes called states and parameters, which are there, which basically tell you what are the states of a thing and what are the parameters of the thing. You have a class policy, which basically has these two things inside it. Then you have a class agent, which has all these different characteristics inside them, and it inherits from it has all the state parameters and policy. One important thing in this long list is the float the boolean active member of this class, which basically tells you whether this agent is active or inactive, basically whether it's blank or not blank. uh, you can inherit from these classes and make your own agent-based model as you like. So this policy can be anything from an RNN to an if-else statement to whatever comes to your mind. And because of AutoGrad, you can just differentiate through them as well. Finally, you have this class agent set, which is collections of this agent. And here you have, just consider this as an array of agents. And then how you make agent set is by using the VMAP, which I just showed you. So you have this array of agents, and then finally you have these functions which you can use to manipulate this agent set. Also, because this so this is like the main crux of the framework, but also these agents act in a space, right? Like these agents are born, die in a particular space. Space can be like continuous world or a grid world or a network of paths or something. So here's as I have made the continuous world right now, but I'm in the process of making grid world and the network world. So you can have things like points, rays, walls, and you can basically do you can see if a ray is colliding with the wall or other agent. So this will be used to model different sensor models, and this will be used to model whether the agent has crossed the boundary or not. In principle, what you can do is form like custom mazes through which agents can move, and custom arenas. Uh, mm, so that was for FORAGAX. Now I just like to walk you through the motivation why I got into this. Uh, my PhD is about modeling foraging tasks and trying to see how agents just keep learning continually and survive, maintain their homeostasis through the task. So what is foraging again? It's just like searching and gathering resources from the environment. It's the most ancient and ubiquitous activity which exists in the natural world. So, right from bacteria to complex creatures like elephants, everyone forages. Uh, it abstracts away the details, yet it is complex enough for this sort of continual intelligence to evolve. For example, you can forage for food, you can forage for information, you can forage for almost anything. And it has known mathematical solutions in the form of marginal value theory, the IFD theory. For example, the marginal value theory is like when you're eating from a particular patch of food, at what point do you stop eating there and migrate towards a different food source? Now, this can be extrapolated in so many ways, right? For example, if you're solving a particular problem using a particular solution, at what point you give up that solution, that approach of solving the problem, and then use a different approach. For example, you are going around the poster session, at what point you stop listening to a particular poster and go on to listen to other posters. So you're foraging for information here. So I began by modeling one agent which forages between these two food sources. Now, this may look simple, but there is a lot of dynamics which is happening under the hood. For example, this agent's brain is an RNN, the food source is having Lotka-Volterra dynamics inside it. But what we saw, okay, here. So, yeah, the food source has Lotka-Volterra dynamics. The agent brain is a continuous time RNN, and there's a double integrator which is moving the agent. But anyways, the bottom line is what we saw here when I take like one neuron from these agents and I analyze the neural activity of this neuron, you see this evidence accumulation mechanism arise. Now, what is evidence accumulation? The activity of the neuron, the neural firing rate, if I may, rises to a particular level, reaches a particular threshold, and when that threshold is reached, the agent decides to move on. This has also been seen in macaque monkeys in work by Hayden in 2017. So just to show what was working there is like you have this environment, you have this resource following this Lotka-Volterra model. You have different resources in the world. You have an agent. Agent's brain is a dynamical system for people who know a bit of neuroscience. It's a Wilson-Cohen model here. Z is the firing rate, but if not, just consider Z as the state space of the brain. So x dot is fx of u, and u here is the observation coming inside the brain. The agent is moving by a double integrator, which means acceleration times time, speed times time, distance. Now the firing rate controls the acceleration of the agent, which says how much resource will be eaten depending on the position, hence depleting the resource. The observations of both the model go inside the brain, and then you can just do back propagation through time to say, okay, this is the optimal, this is how you forage optimally. But now I wanted to step up, because what about things where you have many agent interactions, the environment is not known, you go there, someone comes there and eats your food. I was inspired by these two work. One is the JAX example from David Ha and team, where you have this water world example. These agents cannot see the entire thing, and you have these rays being emitted through the agent, and they see food and poison, and they learn to not eat poison and eat food. And the second example is the JAX by Eleni Hammond and Hammond. Here, the really interesting thing is uh, uh, it's an evolutionary algorithm which has no resets. So, for example, if you have programmed in evolution, you have resets, right? CMAES has, okay, generation one, generation two, generation three. But here there's no concept of generation. It's like how evolution happens in real life, where where agents just die if they've violated their homeostasis, and agents who have lived long enough just have a chance to reproduce. So the population size can be dynamical. It can go up, down, up, down, up. It can increase or decrease. Uh, Now I had the same setup which I had, but instead of having backpropagation through time this time, first of all, I had to change the agent model with the ray casting, where you have rays emitted in the environment and the agent can sense other agents and the food resources. And then you have this evolutionary algorithm, which I just told, deciding what the parameters should be. And here you can see a simulation with 1,000 agents with a random search. So you see these agents. So the green circles are food sources. This red and blue circles are the agents. And you can see they haven't, they just are moving around randomly in the environment. But with the algorithm itself, you see these agents have learned to follow the distribution of the resources and be in the vicinity of these resources. And here you have the life expectancy in these two simulations, where the evolutionary strategy outperforms the random search. Uh, I benchmark. So of course, these simulations were running on FORAGAX. I benchmark these, and then here you have like it's really fast. This speed actually depends on how complex your each agent is, but it is faster than most of the frameworks out there. In the future, I want to improve this framework by including grid and the network spaces, reinforcement learning algorithms, different setups. And in terms of the application, I want to change the Wilson-Cohen model with different neuron models or different learning approaches, etc. That was it. Thank you so much.